this question is difficult, okay? But let's go ahead and give it a try. The first question, 3.1, we're supposed to define the term boiling point. So boiling point is the TP at which the VP is equals to the ATP, right? So the temperature at which the vapor pressure is equals to the atmospheric pressure. 3.1. Let's take a look at 3.2. In 3.2, write down the conclusion that can be made for curve P. So let's go ahead and read through our question statement and sort of figure out what is happening. So the relationship between boiling point and the molecular mass of aldehydes, carboxylic acids, and primary alcohols is investigated. Curves P, R, and S are obtained. All compounds used are straight chain molecules. Right. And then write down the conclusion that can be made for curve P. As we can clearly see, as the molecular mass increases, the boiling point is increasing. So that is the conclusion we can make for curve P. Well, the same is true for curve R and the same is true for curve S. As the molecular mass increases, the boiling point also increases. Why is that the case? We're going to address that sometime later. That is 3.2. 3.3. Explain the answer to question 3.2 in terms of the structures of the compounds. Okay, so now we actually have to support why we are saying that as the molecular mass increases, the boiling point increases. Well, not support, but justify why that is the case. So let's go ahead and try doing that. Okay, so when we're told that we have straight chain organic compounds, right? As the chain is increasing, the London forces are increasing. Okay, so that is the reason why when the molecular mass is increasing, the boiling point is increasing. It is because when you increase the number of carbons on your straight chain, the London forces are going to be increasing between those carbons. So that is the reason we're supposed to give for 3.3. I wrote it down. It says, as the chain length increases, the London force increases, and the boiling point will increase as a consequence because the intermolecular forces, the strength of the intermolecular forces is increasing. That is 3.3. 3.4. 3.4.1. Curve R represents alcohols. Well, we can deduce that curve R represent alcohols without being told. We can deduce that because we have an alcohol, we have a carboxylic acid, and we have aldehydes. We know which compounds consist of which intermolecular forces and which intermolecular forces are stronger than which. We know all that. So yeah, and they're telling us, but we already know. They don't have to. Okay, and then 3.4.1, which homologous series is represented by curve S. So we have aldehydes, carboxylic acids, and alcohols. We know that R is alcohol. Why is R alcohol? Because we have one side of hydrogen bonding, and S is aldehyde, right? Dipole forces. And P is carboxylic acid, where we have two sides of hydrogen bonding. Okay, so this is our acid, this is our carboxylic acid. What is the question saying? Which homologous series is represented by curve S? Aldehyde. Our homologous series is aldehyde. Aldehyde is the homologous series. Okay. 3.4.2. Explain the answer to question 3.4.1 by referring to the strength of intermolecular forces. So, okay, this is the train of thought. Between carboxylic acids consist of two sides of hydrogen bonding. Alcohol consists of one side of hydrogen bonding. Aldehydes consist of dipole, right? hydrogen bonding is stronger than dipole-dipole. So for the same molecular mass, aldehyde should have the lowest boiling point compared to alcohols and carboxylic acids. So that is 3.4.2. Let's move ahead. Okay, we're moving up and not down. So we have 3.5. Let's take a look at 3.5 and hear the stories. 3.5.1, write down the molecular mass of the compound with a boiling point of 97 degrees Celsius. For curve R, the molecular mass of the compound with a boiling point of 97 degrees Celsius. So let's go ahead and have a look. So here we have compound R. These are our boiling points on the y-axis. So let's go ahead and identify 97. 97 should be somewhere here, right? That's where we should have 97. And the molecular mass between 50 and 70, so that is 60. So the answer to 3.5.1, we have 60 grams per mole. 3.5.1. So a straight chain alcohol with a molecular mass of 60 grams per mole. Okay, so let's see. We have methanol. What else? We can also just write an equation for this. I think we can write an equation. Let's see. For an alcohol, we know fully well that we are supposed to have CnH2n plus 2O. Okay, this is the general formula of an alcohol. CnH2n plus 2O. We know that the molecular mass of carbon is 12. So we can say 12 multiplied by n plus that of hydrogen. So hydrogen, we have 2n plus 2. Okay, so we're going to have 2n plus 2 plus that of oxygen. Of oxygen, we have 16. Okay, this is equals to 60. So let's find the value of n in attempt to finding the alcohol with the molecular mass of 60. So we're going to have 12n plus 2n, that will be 14n. 2 plus 16, that is 18. This is equals to 60. So I have 14n being equals to 60 minus 18. 60 minus 18 should give us 42. So n is equals to 42 divided by 14. I think this is supposed to be 3. Okay, let me just verify if it is indeed 3. 4, 4, 4, 12, 2 plus 1, 42. So, right, n is equals to 3. So we know that our alcohol is C3H3 multiplied by 2, that is 6, plus 2, 8. So 3 C3H8O. This is propanol. This is propanol. So there we go. We have identified the alcohol. I'm sure there's other ways you can use to identify alcohol, but that is just, yeah, the approach I'm deciding to take. 3.5.2. 3.6. Two compounds A and B used in this investigation have a molecular mass of 74 grams per mole. A has a boiling point of 118 degrees Celsius and B a boiling point of 142 degrees Celsius. Explain the difference in these boiling points by referring to the structures of these compounds. Okay, so we're looking for two molecular mass, two compounds. Okay, so let's focus on compound A. Compound A has a molecular mass of 74 grams per mole, and then it has a boiling point of 118 degrees Celsius. So let's identify what A is first. Okay, so let's go to our graph. The molecular mass is 74. How many blocks do we have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so we have 10 blocks between 70 and 90. So 1, 2, 3, 4, 5 should give us 80. So we have 80 right here. So that tells me that, let me see. That tells me that 1, 2 should be 74. So if I want to find a molecule with a compound with a molecular mass of 74 grams, then I need to draw a line like that. So, okay, we have 74 grams per mole and a boiling point of 118. So where can I find it? 118 here. Okay, I think I find it on the alcohol. Okay, let me erase here so that I can see what is underneath. I think I find it on the alcohol. This right here should have a boiling point of around 118. So compound A is an alcohol. I know that for sure. It cannot be compound. It cannot be S because S is way below 100, and it cannot be P. It cannot be on the line P because you can see it is very close to 150. So A is the alcohol. Let's take a look at B. What is the data I have for B? So B also has a molecular mass of 74 grams per mole and a boiling point of 142 degrees. Okay, so 142, we can clearly see that it is this one that we have up here, which is our acid. So B is the acid. So what does the question say? The question says, the question is up here. The question says, explain the difference in these boiling points by referring to the structure of these compounds. Okay, so we have the alcohol and the acid. In alcohols, we have one side of hydrogen bonding, while in an acid, we have two sides of hydrogen bonding. The intermolecular forces on the acid will be stronger than that on the alcohol, requiring more energy to overcome the intermolecular forces. And that's a consequence. We're going to have a higher boiling point on compound B, the acid.